Okay, in this section we want to discuss permutations and combinations. This is a little bit more classical probability. Some of you have probably heard a lot of these terms as well. So what is a permutation? Basically, the number of permutations of n different things taken all at a time is n factorial. So that would be 1 times 2 times 3, etc., times all the way up to n. If you have n given things, and you can divide those into C classes of alike things that differ from class to class, then the number of permutations of all of these things taken all at a time is n factorial over n1 to nc, where n1 plus n2 plus so on plus nc is equal to n. And the subscript j will be the number of things in the jth class. So basically, this denominator is inclusive of all possible classes. So if a third of people are under 5'9" and a third are over 5'9" and under 6'4", and a third are over 6'4", then that would be 3 classes. So as an example, if a box contains 6 red balls and 4 blue balls, the probability of first drawing the red and then drawing the blue is 6 factorial times 4 factorial over 10 factorial, which is 0.5%. A permutation of n things taken k at a time is a permutation that contains only a subset k of the n given things. So, for example, 2 possibilities would be the same k elements in a different order. So let's say we have the letters A, B, and C. If we take those 2 letters at a time, we have A, B, A, B, A, B, A, C, B, C, B, A, C, A, C, B. So even though C and B contain the same elements, these two, they're in a different order, so it would be considered a different permutation. So a permutation of n things taken k at a time with repetitions is an arrangement by putting any given thing in the first position, some given thing in the second position, and then continuing until k positions are filled. So for A, B, and C, there are 3 squared because it's if you take 2 letters at a time, there would be 3 things taken 2 at a time. It's 9 different possibilities. So we would have the preceding 6 permutations as well as AA, BB, and CC because we're allowing repetitions. So the number of different permutations of n different things taken k at a time without repetitions is given by this general formula, n factorial over n minus k factorial. With repetitions, it's given as n to the k. So here's an example. If we have an encrypted message and the letters are arranged in groups of 5, and those are called words, from this theorem we can see that we have 26 letters of the alphabet. If we take those in groups of 5 and we allow repetitions, then our number of possible permutations is 26 to the 5th. If we allow each letter no more than once, then we have to use our other formula, 26 factorial over 26 minus 5 factorial. And you can see the possibility space is smaller. Number of different combinations of n things taken k at a time without repetitions is illustrated with these parentheses n above k. That would be n factorial over k factorial times n minus k factorial. And with repetitions, the top n is replaced with n plus k minus 1. The bottom k remains k. So we would just substitute for n factorial up here. We would substitute this term, n plus k minus 1, whatever that is. So if we have 5 light bulbs, the number of samples of 5 light bulbs that can be selected from a lot of 500 bulbs is, so we have 500 possible bulbs, and we're going to select 5, so it's 500 factorial over 5 factorial times 495 factorial. So there are 255 plus billion possible permutations that could occur there. So by definition, 0 factorial is equal to 1. So we can compute variables recursively, given certain values. If n becomes very large, then the function becomes very large, and we can make an approximation of n factorial as being the square root of 2 pi n times n over e to the power n. This means, this approximate sign means asymptotically equal, so when n gets very large, these two formulas are equal. So it's a common useful formula. So here's some comparisons of our exact formula and Stirling's formula. And as you can see, the larger the value of n becomes, the smaller the error in calculation. Okay, the binomial coefficient. Binomial coefficients are defined by the following formula. So you have parentheses a over k. So that's going to be a minus 1, a minus 2, and so on, all the way down to a minus k plus 1 over k factorial. And then the numerator is going to have k factors. If we have a over 0, then the definition of that is 1, and 0 over 0 also has a definition of 1. So for the integer a equal n, we would have n over k, which is the same as n over n minus k. That's when n is greater than 0 and k is between 0 and n. So that would be the binomial coefficient. Okay, let's go ahead and, since that was kind of a short series of definitions, and let me say that we're not going to use a lot of that in class until we get to binomial distributions. I just want you to have seen it so that you have some familiarity with what the terminology looks like. Random variables and probability distributions, on the other hand, is a pretty significant and important part of what we want to talk about. So when we started this chapter, we looked at a histogram, and we saw that you could sample some data and that there was some randomness or variation in the outcome. And so part of what those show is they show either an absolute or a relative frequency of how often those data values occur. So a probability distribution, or just a distribution, does not show the values of the data, but rather they show the probability that an event will occur in an experiment. So if we observe some variable x and it's a random variable, then the value it assumes in the next trial is based on chance or randomness. So for example, if you roll a die, you could roll any number from 1 to 6, but you don't have any idea which one is going to show up next. So the number of times the die turns up is a random variable. Let's say we also are defining a different kind of x, meaning we have rubber bands and we're going to stretch those rubber bands until they break. The value at which they break is going to be different from rubber band to rubber band, so that's also a random or stochastic variable. If we count cars on a road, or any number of different things, there you have a discrete random variable, and you're going to get some kind of distribution. If you're making a measurement, like we measure voltage, rainfall, hardness of steel, you have a continuous random variable, and you're going to get a distribution. So whether it's continuous or discrete, this distribution of x is defined by a distribution function. Now, this terminology can vary from textbook to textbook and field to field, and sometimes this f of x is called a cumulative distribution function, and in fact that is what I've always referred to it as being, whereas a distribution function to me has always meant something different. So what this means is that this f of x, this is the probability that in a given trial the value of the sample that you're sampling will assume any variable that's not greater than some x. So you're incorporating all the values that came before. So let's say I want the distribution function, say at 10. Then what that is that's the sum all sort of the cumulative probabilities that the value was 1 and 2 and 3 and 4 and so on. So what's left after 10 would be the probability that it's greater than 10, if that makes any sense. So a random variable is a function that's defined on the sample space of an experiment, and it's a real valued function. So for every number a, the probability that x is equal to a, x assumes a is defined. So this p of x equal a is just the probability that x assumes the value a. And then if you have some interval, the probability that x lies within that interval assumes that all the values in the interval are defined. So we obtain this formula for probability that corresponds to some interval of x lying between a and b. And notice here that we're putting a hard greater than sign here. So x has got to be greater than a, but it could be equal to b. So it lies between a and b, but could be b. Then basically the probability that x lies in that interval is the function, is probability of b, or the density function of b, distribution function of b minus distribution function at a. Discrete, a random variable is discrete if it just assumes a finite number of values. And those values are called the possible values of x, and they all have positive probabilities. Discrete distribution of x is determined by the probability function little f of x, where if x is within that possible value set, you have some p sub j probability for each possible x, and it's 0 otherwise. So for example, if this were a coin toss, x could assume values 1 through 6. In that case, f of x would be 1/6 for each one, because in a fair toss there's an equal probability. But f of x being 7, or x being 7, would have 0 probability. So you'll get discrete probability values. So if you take those discrete probability values and you sum them up, the point where you are at x is the sum of the distribution function is basically the sum of all the probability values. So here's an example of the number of times a fair die turns up. So we're going to let x be 1 through 6. Each one of those has a probability of 1/6. So if we plot f of x, which is the probability at a given value, then we see that from 1 to 6 we have 1/6 occurring 6 times. If we now plot the distribution function f of x, what it's doing is as we cross over each potential value, it's jumping up to that probability. So when we get to 1, we're going to jump up that the probability of rolling a 1 is 1/6. When we get to 2, now we're looking at the probability function. Okay, we're looking at the distribution function. So by the time we're at 2, we've already incorporated 1. So by the time we're at 2, we're 2/6 of the way to incorporating 100% of all the values. And so this is it's a sum of the individual probability occurrences. Now you can envision that as these distinct values become continuous, what happens? Each value, the space between each value gets smaller and smaller, and this stepwise curve is going to become continuous. So if we had all of these values in between also possible, then obviously our probability would be a lot smaller. Our distribution function would be smoother instead of stepwise. So here's another example. This is that the sum of two numbers of 2 fair dice turn up. So how often would that happen? So this is just a plot of the sum of two numbers when two dice are rolled. It turns out to look like this. Here's how you get that. The fact that the sum would be 2 would be 136. The sum being 3 would be 236, and so on. So the distribution function then, so this is the probability function. The distribution function basically is summing up at each integer value the total probabilities that have occurred in the past. So in your distribution function, as it's defined in this book, you're going to end up at 1 by the time you reach all the possible values, and it'll just stay at 1. Some people refer to this as the probability density function because it's basically showing you at a given location what's the probability that that occurs. So this is a formula that we've seen before. If you have a discrete distribution, the probability that x lies within a and b is the, so let's go back to the previous slide. So that might be like the probability that x lies between 5 and 8. So you would take the probability distribution function value at 8 and you would subtract the function at 5, and that's what you would get excluding 5. Otherwise you would have to go down to, if you wanted to include 5, you would have to go down to 4 when you do this subtraction. And you could also find that by summing the individual probabilities of each value. So once again, we would expect the sum of all the probabilities to be 1, and so we would expect our distribution function to come out to 1. So here, in fact, is exactly that example. Compute the probability of a sum of at least 4 and at most 8. So we would take the probability at 8 and we would subtract the probability of 3, because remember, this is not inclusive of 3, this is greater than 3, less than or equal to 8, and that would give us our probability. So this is a more important concept. We're talking about discrete values here, but when we start talking about probabilistic testing and statistical testing and determining whether data sets meet certain statistical criteria, this concept of the probability of lying between one value and another value becomes very important. Okay, the rest of this is primarily, we're going to stop here because of the length of the video, and then we'll pick up with discussing continuous random variables and distributions. So basically this is just going to be a generalization of the discrete random variable and distribution to continuous space.